Hey guys, guess what? We're going to move on to 9.3 today, which is all about significance testing for population means. So now we're talking quantitative data, not qualitative. So keep that in mind as we're going. Numbers, means, X bar, all of those things. So that's what we're going to be doing today. In this video. Okay, so our SWBAT for today is to check conditions for carrying out a test about a population mean, and if the conditions are met, my battery is low. If conditions are met, conduct a one sample t-test for a population mean, mu, or possibly use a confidence interval to draw a conclusion about a two-sided test. So we're going to look at two different scenarios. Okay, so here's the deal. When you have a simple random sample with an unknown mean, right, and you want to test the validity of somebody's claim for a mean, you could have three different scenarios. The first one is mu is larger than the null hypothesis, and so you're just testing one side. Mu is less than the null hypothesis, so you're testing the left side of the sampling distribution, or possibly that you're just trying to test if the mean is different from the null hypothesis, from the claim. So then you have a double-sided. So if you're doing means, generally you're only going to be using t distributions, not z distributions, just because you only use the z distribution for means if you know sigma. And if we don't know mu, we rarely will ever know what sigma is. So usually we're going to use the t distribution. So that's our statistic for this scenario. T is x bar minus mu over the sample standard deviation divided by the square root of n. All of that's on your stats packet too, so you should be good to go there. Okay, so I'm going to reiterate the four-step process for all significance tests. It's the same thing that we did the last time with proportions, except this time it's with means and quantitative data instead of qualitative data. But the process is the exact same thing. So number one, you state your hypothesis, null hypothesis and alternative hypothesis. You talk about your significance level and what parameters you're using, okay? And then you have to, state all of those things in context. And perhaps maybe the test that you're going to use too, unless you do that in the plan step. Doesn't really matter where you do it, you just have to say what you're doing. Two is in the plan. You want to check your conditions, obviously, and your conditions are the same as they were when you're doing confidence intervals as well. And it's also the same, kind of the same as when you're doing proportions, right? Random, normal, and independent. But the problem is, in this case, if n is less than 30, right? If your sample size is less than 30, then you have to plot the data and see if there's any variations from the norm, right? Is there skewness? Are there outliers, etc.? So that's what you need to do if n is less than 30 to see if you can use the t distribution. And then, unless you have sigma. If you have sigma, then you don't need all that stuff. You just need n greater than or equal to 30, and then you use the z test. But that doesn't really happen very often. So anyways, you're going to do check all of your conditions, and then find your test statistic. And then we plan, and then we do our do step, right? Which is do our calculations and actually figure out what our p-value is. In this case, we're generally going to be doing t because it's means, and usually we don't know sigma. And so we have to use our t distribution instead of our z distribution. And then, therefore, you need your degrees of freedom as well. Okay, and then once you find your p-value, then you can conclude in context. So let's do a couple examples so you can see what this looks like. Okay, so this next problem is about classic rock station. Oh yeah, oh yeah. So you've got a classic rock station. They claim to play an average of 50 minutes of music every hour, which most stations tend to do, but it seems that like every time you turn on the radio station, there's a commercial. And so we want to test whether or not their claim is actually true, because we kind of think it's false. So, to investigate their claim, you randomly select 12 different hours during the week and record the radio station and how many minutes of music they actually play in each hour. So here are the number of the minutes in each of the hours. And then your task is to determine whether or not the radio station's claim is an overestimate of what they truly play or not. Okay, so step one, state. What are your hypotheses? What are your parameters? And what test are you actually going to be doing? So we actually don't really care much if the amount of playtime is more than 50 minutes, because then we'd be happy. So we want to only check one side. If the playtime that they claim, 50 minutes, is less than what they claim is actually more than what it truly is. So we have a one-sided t-test for means. Alright, so we've got our state down, we've stated our hypotheses, we've stated our significance level, and we've stated what test we're going to be doing. We're doing a t-test because we don't know sigma at an alpha level of 0.05. Now we need to plan. Random, is it normal, and is it independent? And so for the normal condition, because it's means and our sample size is less than 30, we're going to have to actually graph the data. So here we go. Condition 1, was the sample random? And if you look back up, right, it says you randomly select 12 different hours. So yes, we can assume, not assume, but because it tells us that we have a random selection, that condition's met. Okay, for normality, since we don't know sigma, we need to determine, right, since we have 12 hours, that's less than 15, so we really need to graph the data and not have any departures from normality. So no skewness, no outliers, nothing bad or ugly like that. So we need to graph it first. So let's do that on our calculator. Alright, so we put all of our data into list 1, okay, all of our minutes of music play. And then we go to stat plot, and then we want to either plot a histogram, a box plot, or a normal probability plot. It doesn't really matter which one. I tend to, I don't know, I don't really care. Let's do a box plot with outliers. We want for list 1, and then we're going to graph that. So when you graph the data, it's a little skewed right, but it's not that bad. It's approximately symmetric. If you did the histogram or the normal probability plot, it would be reasonably symmetric or approximately linear if you're doing the normal probability plot. So we can continue, check the last condition and then continue with our calculation. And lastly is the independent condition, which is n less than or equal to 10% of the population. So we assume, I think pretty accurately, that there are more than 120 hours of radio played. Yeah. So our conditions are met. Woohoo! So now we can go to the do step and just do all of our calculations. So in order to do our calculations, we need the standard deviation of the data. So we just go to stat calc 1 bar stats of my first list, right, which is where I put my data. So now I have my standard deviation, S sub x, which is 2.81096 approximately, right here. So then when we plug everything in, our sampling distribution has a mean of 50 and a standard deviation of 0.8115. Then we need to calculate our test statistic, and keep in mind that we are on the t distribution with degrees of freedom n-1, so 11 because we had 12 data points. And so we need to figure out what our test statistic is. So we find t to be negative 2.59, and then we need to find the probability that t is less than negative 2.59, which is actually this exact same thing because it's symmetric. And remember, the t distribution table counts the positive side of things. And so that's the same thing as the probability that t is greater than positive 2.59. So then we go to our t table. We look at our degrees of freedom 11, and then we try to find our 2.59. Okay, so the t table isn't as detailed as the z, so we know it's going to be somewhere between 0.01 and 0.02. And at an alpha level of 5%, we would reject the null hypothesis either way. So then we reject the null hypothesis and we say we do have statistical evidence to say that this radio station actually plays less music than they claim they do. And there's your conclusion written out for you. And to do the same exact calculation in your calculator, you go to Stat Tests, and we did a t-test, but not with proportions, so we want just the normal t-test. And then you can enter your either statistics or your data, depending on if you entered data into a list, which we did. So let's do that. And we put everything in list 1, and we want our null hypothesis to be 50. So we enter that, enter list 1, and then we want our mu to be less than 50, and we calculate, and we get our p-value 0.013. So that's cool. All right, so for example 2, we are talking about widths of little plastic cubes, and the claim is that they're 29.5 millimeters wide, but the actual width varies a little bit. And so basically what they wanted to figure out is with this sample of 50 cubes, which has a mean of 29.5 millimeters, a standard deviation, a count of 50, so that means, there's 50 samples. Standard deviation 0.087, standard error 0.0124. And if you look at it and if you actually calculate it, you get your standard error by taking your standard deviation divided by the square root of n, which is 50. So you can actually just use this to calculate your p-value. So since we're not testing whether the width is less than a certain amount or greater than a certain amount, we're just going to test if it's not equal to. So this is a double-sided test. So let's set up our state and plan. So there's our state. Our plan is the same thing. Is it random, normal, and independent? And in this case, the normal condition, we don't have to graph anything because n is greater than 30. So yay, we're happy. So we can check off all of our conditions, and we can go on to actually calculate our p-value. So here's our situation. We've got our standard deviation given to us, our mean given to us, and our mean of our sample, which is 29.49, given to us. We just need to find the probability of this. And since it's a two-sided test, we're going to have to do double that because we need to know the probability of getting something on the right-hand side as well. So let's figure out our test statistic. So we calculate our test statistic t to be negative 1.0161. So we want to find the probability that t is less than or equal to that, which is the same as the probability that t is greater than or equal to that. So then we have to pull out our t table, and degrees of freedom is 49. All right, so degrees of freedom is 49. If you choose the table, you have to round down. You can't round up to 50 because then you'd be cheating and saying your sample size is larger than it is. So we would say that our probability here is somewhere between 0.15 and 0.20. This is a two-sided test. You have to multiply by 2. And since that is greater than alpha, which is 0.05, we fail to reject the null hypothesis. So there's your conclusion. If you want to do it in your calculator, I'll show you that as well. Again, you go to Stat
and tests, and you're doing a t-test. This time you're entering stats because you didn't have data. So you enter all of your information, hit enter, and voila,